All hundreds of my lives.
I mean, at least I think so.
No,
Okay, let's start. So there has been some request to decide the midterm date, and I think before the spring break you have the midterm. So when is the spring break? Module spring. So the spring break, don't be too excited about exam. The spring break is on March 4th, which is February. March 4th, still Sunday? Starts on a Sunday? That's a waste, one day wasted. So for March 4th, so we will have it on 28th? February 28th. Okay, so let me post an announcement. Okay, so we have decided February 28th in class, the regular class times. So what? So in class, close book and notes, and you have one cheat sheet, both sides, and make sure that your cheat sheet is this size, not like a poster. And you bring your calculators. Bring your calculators. So do you have? Oh, so there was a question last time that monotonous and non-monotonous. I was going to say something that the purity matrix, right? Purity matrix is monotonous or non-monotonous. So it depends upon how you see the purity metric. So if you look at the purity metric, on the x-axis is P, which means fraction of records that belong to one of the two classes. And on the y-axis, value of impurity measure. So any P greater than 0.5 is not useful. Why? Because then you can interpret it as being fraction of records that belong to the other class. Right? Fraction. So if you have class A and class B, fraction of record that belongs to class A, if it goes more than 0.5, then that means the other parts belong to me. So then P changes. So if you look at the half of this picture, then it is monotonous. But yeah, if you look at the full picture, then if P is defined as that, one of the two classes, then it's not monotonous. Any questions or any clarifications you need before we move on? Any questions? Okay, so we were talking about, let's do a little bit of a recap, not a lot, but a little bit of recap. So we were talking about decision trees, and we said that there is a Hunt's algorithm that we can use to expand a decision tree. Hunt's algorithm is very simple. So what you do is somehow select a root node, and then based on that root attribute that you have selected, you split up the data set. Now if in the one split you see that this data set has a pure class, which means this is not a mixture, don't split that child node again. Just keep it there. Then there can be another case that that child node has nothing, it's empty. If it has empty, just give it a default class, do nothing. But then there can be the third case that this child node has a mixture of classes. In that case, you need to split. So Hunt's algorithm says that, okay, find an attribute. It doesn't say how, right? It doesn't say how do you find an attribute. It just says find an attribute and again do the same thing, the split. Right? That's basically Hunt's algorithm. It's very simple. Now the devil is in the details. So how do I find an attribute? Even if I find an attribute, there can be multiple different ways I can split it, right? If I have a nominal attribute, I can have split with respect to all the options, or I can club different options and make a binary split. If I have a continuous attribute, I can have infinitely many splits, right? So which one do I choose? So we defined, okay, we have to define some purity metric. We said that, okay, what is a purity of a split? We defined several Gini index, entropy, and misclassification error. So these have certain values. Gini index has this expression, so you have to just remember this expression. Then entropy, okay, no, Gini index or any of these purity measures can be used for a node or can be used for a split, right? So you can determine the Gini index of a node, entropy of a node, or misclassification or error of a node, or you can also find out Gini index of a split, entropy measure of a split. So how do you do that? So for a node, follow those equations: 1 minus pjt square and summation over all different elements in the node, right? So that is not, no, what is J? Oh, all different classes, sorry, not elements. So classes, so summation over all different classes, you get the Gini index. But then how do you find it on for a split? Basically, you take a weighted sum of the purity matrix. So weighted sum means, how do I weight? So the number of elements that are in a particular split divided by the total number of elements in the parent, right? So you take that weight and multiply the Gini index, sum it up, and that's how you do it for all the purity metrics, right? So now what you do, how do you select the split? Whichever has the least, right? Whichever has the least value, you use that. Why do you have whichever has the least value? Because you want to measure the gain, right? Gain means what? The purity of the root or the purity of the parent minus the purity of the child, right? Or rather the impurity of the parent minus the impurity of the child. So that has to be positive because the impurity of the child has to be less than the impurity of the parent. That's the whole purpose of doing the decision tree, right? So that's why you want to maximize that difference. Impurity of parent minus impurity of child, you want to maximize it. Now it turns out that impurity of parent is constant because it depends upon how many elements you have for the parent node, right? So that never changes. So basically you end up minimizing the impurity of the split, right? That's why you want lower values. So you want lower values for the impurity measure. So these are all different impurity measures. We have already talked about this, and then we talked about entropy and all that, misclassification error. We saw how these three metrics change, right? We talked about the gain. Now the important thing that we talked about is that so we talked about the gain, but the gain actually cannot identify how many splits are there, right? So what is the purpose of the gain? The purpose of the gain is to reduce the impurity of the split, right? Now one way to reduce the impurity of the split is have one leaf node for every data point that will have the least amount of impurity, right? Every class is pure, but that is not what we want, right? We don't want to increase the number of splits to that extent. So the gain doesn't give us that picture. Instead, what we find is the gain ratio, which means gain divided by some information regarding the split, the size of the split. So we said, okay, what we will do is we will take the gain and divide by the split info. Right? Split gain divided by split info. And what is split info? Is that value, ni by n log ni by n and a summation. Right? If you look at it, it is kind of the entropy of the split. Right? It turns out to be the entropy of the split. So that is what we discussed last time, and then we were trying to discuss overfitting and underfitting, right? And this came up when we were trying to understand when do I stop the tree? When do I stop the tree building process? Right? That was the question I asked, or we asked. So turns out that if I don't stop at all, then the tree, there can be a case that the data is so organized that, so misorganized, that you end up with a leaf node for every data point. That clearly is overfitting, right? Because if you give a test data, right? If you give a test data, then it has nowhere to go. It will fall in an empty class. And it will have the default class level and will have 100% error. Right? So we talked about generalization error, and it is coming a little bit later, but I want to talk about it right now. So generalization error we talked about, and it has three components. The first component is normal data noise. Right? Data noise you cannot do anything, you cannot reduce. It has to have it has to be there. Then there are two components, bias and variance. And bias and variance we discussed. It's related to model complexity. So you can have simpler models or complex models. Now, the notion of simple model and complex model is very difficult to quantify. Model complexity is very difficult to quantify. And this model complexity will be dependent upon what type of machine you use. For example, if you use decision trees, model complexity can be height of the tree. Right? That is the measure of model complexity. On the other hand, if you use neural networks, what can be a measure of model complexity? Number of layers can be one, or in one layer how many neurons, that can be one, or connections. Do you have a feed forward or do you have a recurrent, right? So those are many different measures of complexity, and those are totally different from decision trees. On the other hand, if you have support vector machines, what can be complexity measure? Support vector machines are difficult because they are lines. Everything is a line. So how do you know? How do you characterize complexity?
Number of boundary points.
It's a line. There are no boundary.
Number of support vectors.
Still, it's a line. It's number of support vectors, but ultimately it comes out to ax plus b. So it's just a and b.
Number of dimensions, features.
Yes, that can be one. Number of features, right? Number of the feature dimensions. But that is not complexity of the machine. That is complexity of the data. The data attributes, total number of attributes. So that's not complexity of machine.
Maybe the regularization parameter, however you decide to do the regularization.
What do you mean by regularization?
I don't remember the term, so.
Okay, so let me discuss. So, support, we will talk about that actually, but briefly, to just a peek ahead. So, support vector machine's assumption is that data, whatever data you have, if you increase the dimensionality of the data by adding more and more features, right, then every data set can be classified using a straight line. You can differentiate, if there are two classes, you can differentiate between them using a straight line. So that straight line can be in 2 dimension, 3 dimension, 5 dimension, 10 dimension. In that case there will be planes, but still you can classify using planes or straight lines. That is the assumption of SVM. That is where it works. Now the thing is, often increasing dimensions are time consuming. Right? But that is not model complexity though. Increasing dimensions is time consuming because you have to run the SVM for a long time. Now, one way that SVM goes around that problem is using kernels. Right? So if it sees that, okay, in the feature dimension, I do not see any straight line or do not see any plane, I can apply a transformation on the features. Right? So there are many different types of transformations, like RBF, and some others are there. Right? So those kind of transformations I can apply, and in the transform domain I will see that, okay, there is a line. Right? So an SVM with a transformation is more complex than an SVM with a linear, just in the feature domain. Right? So that can be another complexity metric. So complexity of machine is difficult to quantify because it is varying for different types of machines. But if we fix a machine, let's say decision trees, if we fix a machine, then we can say, okay, this complexity is the height of the tree. So now turns out that if you change the complexity, your error, generalization error, can either decrease or increase. And there is no telling. But there is a sweet spot. There is a sweet spot as in, if you have too simple a machine, the generalization is more, generalization error is more. If you have too complex of a machine, the generalization is more. Right? So this is what? This is religion, teachings of Buddha, if you are familiar with it. Right? Buddha says what? Take the middle path. Don't go to the extreme. Not extreme bad, not extreme good. Right? So if you talk about machine complexity, don't be too simple, don't be too complex. Take the middle path. Right? Now the entire life of a person or of a Buddhist goes away with just trying to find the middle path. Right? So see how difficult that is. So same for machines. Right? It's a very difficult problem to find the middle path. Same for these kind of machines. So that is a fundamental research topic of machine learning systems. How to find the sweet spot. Right? So why is it such a saddle-like graph? So what happens is that there are two concepts, bias and variance. We have talked about this. I'm just repeating. So what is bias? Bias means that the model is so simple that it is far away from the true model. Right? From the true model is far away from it. So if it is very simple, then it will have high training error as well as high test error. Right? And if it is too simple, then if you give it two different training sets of the same phenomena, if you give two different training sets, it will come up with the same model or very similar models. And because it's too simple, it's just looking at one particular characteristic. Right? Now on the other case, if you have too complex of a model, then what will happen is that the model is very close to the true model for that particular training set. So it's so true that it also learns the noise in the training set. So if that is the case, then if you give it a different training set, it will learn that training set's noise. And we know that noise don't have patterns. If it's true noise, it doesn't have patterns. Right? So it won't learn the actual data pattern. So what will happen is that two training sets will have totally different models. It will have very low training error, nearly zero training error, but extremely high test error. Right? So generalization error is the combination of these two, bias and variance. So which means that if you have too complex of a model, the variance increases, the bias reduces. But if you have a too simple of a model, the bias increases but the variance reduces. So these are two contradicting forces. So that's why you have a saddle-like graph. Right? Now we'll come back to this a little bit later and we'll see what is the effect of this saddle point. How do we control the saddle point? So these are examples that the book has given, and this graph we have already talked about, right? Overfitting and underfitting. This is also how we have talked about how noise affects overfitting. Right? It makes unusually complex systems. So we stopped here, Occam's razor. So what is it? It's a very simple postulate that given two models of similar generalization error, you should always choose the simpler ones. And this is why? No specific reason why, but only speculation. The speculation is maybe the complex model is more prone to learn noise. Right? Complex model is more prone to learn noise. Now that's a hypothesis, that's a speculation. No evidence exists. Maybe evidence exists in particular examples, but it's not a general trend. Right? That's why this is not a theorem. So you should always choose the simpler way. So simpler why? Because less work. Right? That is also another advantage. Less work. You don't have and you execute faster. Therefore, one should include model complexity when evaluating a model. So when you evaluate a model, you should have model complexity embedded in it. In whatever evaluation metric you are using, right? You should have model complexity in it so that you can reduce it. Right? So having with the same generalization error, you reduce the model complexity. That's what you want to achieve. So now we come to the estimation of generalization error. So from that knowledge that we have to include model complexity in whatever evaluation we do. So let's discuss how do I get the generalization error. Now the thing is, generalization error has to be done on the test set. It's not on the training set. Right? So generalization we have to evaluate on the test set. But where is the test set? When we develop a model, there is no test set. It's all data we know the class for it. Right? So it is training set, everything is training set. So before even testing the model, how do I know that it has a lower generalization error? We don't. So yes? Somebody wanted to contribute? You can contribute.
K-fold partition of data training.
Yes, so that is one way. That is one way. Partition of data. So have a validation set. Right? Have a validation set, and what are you assuming? What is the underlying assumption when you have validation set taken from the training set? The underlying assumption is the test set has the same distribution as the training set. Right? That is the underlying assumption, which is often true, but often not true. Right? But that is an assumption. So you assume. So what you say is that there are two approaches, optimistic approach and pessimistic approach. So optimistic approach says that, okay, training data set is same as test data set, it has same distribution. So whatever error I have in training data set, that is the error in test data set. Okay? That is the optimistic approach. And then there is a pessimistic approach. So pessimistic approach incorporates model complexity. Right? So it says that, okay, whatever error is there in training data set plus model complexity error. Right? So what is model complexity error? In this case, for particularly decision tree, this does not apply to other machines. But particularly for decision tree, what you can do is you can take the number of leaf nodes and multiply with the weight. Right? So here they have said, okay, 0.5 is the weight. A penalty. You add a penalty term for each leaf node that you have in the decision tree. Okay? So that encodes the model complexity. So pessimistic approach error is your training error plus n times some penalty, where n is the total number of leaf nodes. Okay? So now what you do is you can have a validation test, validation set. So from the training set, as he suggested, that you keep out one set and you call that a validation set, and you pretend as if that was your test. Okay? Now if you might have heard the term cross validation, right? K-fold cross validation and all that. So that stems from this idea. So instead of keeping a dedicated set as validation set, what you can do is you can change this validation set. Right? So you say, let's say the first 2/3 of the data is training, the last 1/3 is validation, right? So then what you do on the next time, so you do the estimation once. Then what you do is you change the validation set to the first 1/3, and you train using the last 2/3 of the data, test using the first 1/3. Then what you do? Then you keep the 1/3 in the middle. You train using the first and the last 1/3, and then test using the middle 1/3. So this is 3/4 cross validation. Right? So that's how you can use the training set to validate. So yeah, that is what this slide is saying. Now the drawback, the problem is you have less data to train. Not only you have less data to train, you have to be very careful in selecting validation set. Right? What if you had a 3-class classification problem? Right? You had a 3-class classification problem, and in your training set you selected only class 1 and class 2 and made the entire class 3 validation set. Huge error. Right? The machine will only train and test class 1 and class 2, it will never recognize class 3. Right? So you have to be very careful about selecting your validation set. Right? You cannot have any set as your validation set. Now that is one way of incorporating model complexity into generalization error evaluation. Now how do you minimize it? The idea is to minimize generalization error. So which means you have to have some way to stop overfitting and some way to not underfit. Right? You have to find some way. So there are pruning techniques. Pruning techniques means there is a tree, huge tree, and you cut the leaves. That is pruning. Right? The same concept here, decision tree. There are two ways to prune a tree: pre-pruning and post-pruning. Pre-pruning means you don't grow the tree at all. Grow the tree to the full length. You don't. What you do is you have a condition and you only grow to a certain extent and stop. Don't grow to the full. That is one technique. The other technique is post-pruning, which means you allow the tree to grow. So you have one of those stopping conditions, that when you have all classes pure, right? That is one stopping condition. So you grow the tree to the full, and then you decide to cut child nodes or branches. That is post-pruning. So how do we do pre-pruning and post-pruning? So pre-pruning is an early stopping rule, which means you stop early. You don't stop after all the classes are pure. Right? So early stopping is what? Stop the algorithm before it becomes a fully grown tree. So typical stopping conditions for a node is stop if all instances belong to the same class, or stop if all attribute values are the same. These two we have seen before. So these are the typical stopping conditions. But you can have more restrictive conditions. Example, stop if the number of instances is less than some user specified threshold, which means you get to a node where the instances are less than 10. Right? You have that threshold 10. You will not split any node with less than 10 items or 10 instances. So whenever a node arrives, 10 instances, even if it's pure, impure, don't care. Stop, don't split it. Right? So that is one way that you can do. Or stop if expanding the current node does not improve impurity measure. Now this is a more effective one. So what it is saying? It's saying is that okay, whenever you take a node and you split it, I expect improvement in impurity. Right? That is why we split. So what you can do is you can set a threshold. You say that if the impurity does not increase by X amount or X%, don't do the splitting. So all these are pre-pruning. Pre-pruning means the tree hasn't yet fully grown. You are still splitting. You are not done splitting yet. So before splitting, what you do is you can do an impurity measure calculation. You say that okay, this is my parent node. Its impurity is something, and then I select all possible splits and I find out the maximum gain or minimum impurity split. I find out. Then I see the gain, and I see that this gain is not even 2%. So then don't split, just stay there, leave it there, impure. So now the problem is, yes, we all know it's difficult to choose the right threshold. So that is the problem of taking the middle path. It's difficult to choose the middle path. Right? So too high threshold underfits the model and too low threshold is insufficient to overcome model overfitting. So too high threshold means you will never split. So if you don't split, you have a simpler tree. So that leads to underfitting. Okay? And if you have too low threshold, then that means you always split. Right? You always split in, you almost go to a fully grown tree. Right? So that leads to overfitting. So which threshold do you choose? That's a big problem. Nobody knows. You have to do it and see. So that is pre-pruning. And the other is post-pruning. Post-pruning means you let the tree grow to its entirety and then trim the nodes of the decision tree in a bottom-up fashion. So which means you start from the leaf nodes. You try cutting the leaf nodes and see what happens. Right? So if generalization error improves after trimming, replace the subtree by a leaf node. So what is happening? So let's say you have a tree and you have 2 leaf nodes, right? And this leaf node has another 2. So you take this leaf node and you cut it. If you cut it, then all whatever was here will go to the root node, right? So if you replace the root node by a single node, you don't split. What is the impurity measure? And versus when you split, right? So if the impurity measure, or no, not impurity measure, generalization error. Sorry, not impurity measure. So if the generalization error improves, then only you change. So generalization error is different from impurity measure, right? We saw generalization error. It's the training error plus n times some penalty. Right? So if you do pruning, post pruning, then the n is reducing. Right? Number of leaf nodes are reducing. So that's why it has the possibility of reducing generalization error, because the number of leaf nodes are reducing. Now, so note that pre-pruning works with impurity measures, while post-pruning works with the generalization error. So these are two metrics. So whenever you do pre-pruning, you look at the impurity measure, and whenever you do post-pruning, you look at the generalization error. Right? So two metrics, two totally different metrics, these two look at. Right? So what is it saying? Post-pruning is that if the generalization error improves after trimming, then you can replace the subtree that was cut by a node. Right? So then what happens? What happens to the class level of that leaf? Because there is a mixture. Whenever you cut, there will be mixture. There will be impure nodes, right? So what happens to the class level? So what you do is you check all instances, majority class, that is the level. Right? So then it goes and shows some examples. So we'll go through these examples when we do midterm review. Right? These examples, I mean, this should be self-explanatory. It's in the book. All those examples are in the book. Let's go through one of them. Let's see. So there are 2 classes, yes or no, and there are 20 yes and 10 no, and the total error is 10 by 30. Right? That is the error. So training error before splitting is given 10 by 30, and pessimistic error is what? So training error that's before splitting is 10 by 30. So this is my optimistic error estimate, right? Because I assume that training error is same as test error for optimistic error estimate. So now what is pessimistic error? So then 10 by 30 that was there already plus 0.5 multiplied by 30. No, what is that? Now why divided by 30? 0.5 multiplied by number of leaf nodes. So we didn't split, so this is just one leaf node. Right? So it's one leaf node, that's why 0.5 multiplied by 1. Right? And it's dividing by 30 to figure out a percentage. so what happens? 10.5 by 30. You don't need to divide by 30. You don't need to divide by 30. You just can compare the whole numbers. Then if you split, let's say the split comes out to be like this, right? If the split is like this, then what is the training and test error? So let's say training error after splitting, let's say it is 9. Right? Let's say you have improved training error a little bit. Right? Now what is the pessimistic error after splitting? So 9 plus how many leaf nodes? 1, 2, 3, 4. 4 multiplied by 0.5, so that is 11. So now you see after splitting, the error increases, right? So if you had cut this branches, then you will only have the node A, right? And that node A has a lower generalization error, right? That's why you should prune. Do you understand this example, or does it need more explanation? Anybody needs more? Yes.
Can you just go over, like, how did you find a training error after splitting?
That's given. Given, I didn't find it.
And it was the training error plus number of splits, and that came out to be 11 by 30. But what do you prove? Because, like,
Oh, you just, so basically this is the tree. This is the tree is given. The A and then A1, A2, A3, A4. The tree is given. Now you are making a decision, okay, should I prune?
okay.
Right? So if you are making a decision, should I prune, then you first see, okay, what was there in A? What is the training error in A? Pessimistic error, optimistic error, both. You find out. And then you say, okay, now what is training error? Now that I have split, what is training error and what is pessimistic error? And you see that, okay, the split has more error, more generalization error. So you should just remove all the split. So just cut all the leaves. So it goes into examples of post pruning and all that. These I am not discussing. These are all numerical examples you will find in the book. Now decision boundary. Okay, this is a very important thing. Although it doesn't seem very important for decision trees, but decision boundary is very it's very important for recent research. Right? So what is a decision boundary? The decision boundary is, let's say you have class A, you have class B, right? In the attribute space you are looking at this, because that's where you are dividing. Attribute space means each axis is one attribute. So if it has 10 attributes, then this is 10-dimensional space volume. If you have 2 attributes, then it's a 2-dimensional coordinate space on paper, right? So what is decision boundary? Decision boundary is some line. It's some line that divides 3, 4, 5, 6, 7, 8 classes. In this class, let's assume 2 classes. Right? It's some line that divides 2 classes. Now, what will you do with that line? What is the significance of that line? There is no practical significance of this line. You cannot argue about anything from that line. You cannot say that, okay, anybody who is outside that line is bad, anybody that is on this side of this line is good. You cannot say it. It's just a line, right? It has no physical meaning. But computers or machine learning systems attribute meaning to it, right? Because when you test with a test input, it attaches meaning to the class boundary. If you are on that part of the class boundary, the machine sees you as good. And if you are on the other part of the class boundary, the machine sees you as bad. So take the example of biometric authentication. You know fingerprints, right? You have finger or iris scan. Many different ways of biometric authentication you can do. So the machine does not know you, is not seeing you. The machine sees you as a data point in the attribute space. That data point may lie on the good side of the decision boundary or on the bad side of the decision boundary. If it lies in the good side of the decision boundary, you get in. You are through customs, you are happy. And if you are on the bad side of the decision boundary, then you wait 30 hours in customs, or you are deported. Okay? Now it's a very big decision that the machine is making. Now what if I figure out the decision boundary? I means a bad person, let's say. A bad person figures out the decision boundary. You give your fingerprint, right? And it falls in the good class. So you are through. But I come in, I take your fingerprint, I know that you are on this side of the decision boundary. How much change should I do so that you go to the bad side? Can I do some simple changes so that you go to the bad side? What will happen? In this kind of example, nothing but you will be deported. But it can have serious consequences in other examples. So you know autonomous vehicles. Right? Autonomous vehicles are here. On me level you can see. So how do they recognize stop signs? They take a picture, they run a machine learning algorithm, and there is a class boundary. On this side of the class boundary is stop sign, on this side of the class boundary is go sign, or go or any other sign. Right? Now there has been a significant amount of research that shows that if I have some graffiti on stop signs, without even, I may not have the intention to change it, but even if I have some graffiti on the stop signs, it can get classified as go sign. It can fall on the go side of the decision boundary. So now the question is, can a malicious entity go into a neighborhood and do some graffiti, some carefully constructed graffiti in every stop sign, so that every autonomous car gets classified as go sign? If I know the decision boundary, I can do it. But that's not the reason you should know the decision boundary. Those are dangerous things. So you should know the decision boundary so that you can stop it. You can stop such kinds of problems. Right? So you have to make the decision boundary complex enough so that these kind of mischievous people don't have an idea of your decision boundary. Right? So that is cutting edge research that is going on right now. In fact, security and privacy, IEEE Symposium on Security and Privacy, we recently had a paper on that, on understanding this kind of machine learning problems. So these are called adversarial machine learning. Adversarial machine learning means typically you use machine learning systems to do what? To recognize, to object recognize, to predict something, classification. But now this has changed. You use machine learning systems to attack other machine learning systems, right? To generate some input that gets classified into your desired class. So there is an attacker who is trying to break the machine learning system. So that area of research is called adversarial machine learning. So how to do some attacks and how to thwart attacks. Okay? So that we cannot really discuss in this class, it's too broad, but that is why you need decision boundary. Now for a decision tree, what is the decision boundary? It's very easy. So if you have a threshold base, it's just a line. Right? It's just the equation of that attribute, y less than 0.47. If y less than 0.47 is what? 1/2 plane of the coordinate space, right? So that's why it's a line. So if you look at this, first root node is x less than 0.43, so that gives me this line. Then the second node says, okay, if it is yes, that means this part. If it is yes, then you use y less than 0.47, so that gives me this part, right? And if it is no, that means this part, then y less than 0.33, so that gives me this line. So this is the decision boundary, very simple. You can also have line as a decision boundary. How? You can have this x plus y less than 1. You combine two attributes. Okay? You can combine two attributes, and if you have x plus y less than 1, that's the line. So decision boundaries can have all sorts of boundaries, decision trees. So again, we come back to the bias variance trade-off. We have already discussed this, so we don't need to discuss this again. This is just showing a graphical representation of what is bias and what is the bias variance trade-off. So what is it? So if you have a data that is, or if you have a model, the model is red, right? Let's say if you have a model that is too simple. No, the right model. The right model is here. It encompasses nearly all data points. So this has low bias, low variance. This is what we want, right? And if you have a too simple model, then it has high bias and low variance. So which means it's totally tangential. This is the model and this is the data, right? If you have too complex of a model, then we have low bias and high variance. So which means here. So you have all these three circles as model and it doesn't work. High bias, high variance, you don't need to look at it. So the book explains using a polynomial fitting problem, and we have already discussed this so much that I'm not going into this example, but if you want, I can later. You read this example, if you want explanation, you can go over it. It's not a big deal. So the bias variance trade-off, that is error on test set, we have already discussed this. So model complexity versus error on the test set. How does that work? So it is saying that, okay, bias decreases always. It doesn't increase. Bias is always decreasing. If more and more complex you have the model, the less bias you have, right? And variance also does not is monotonous. It's not like increasing and decreasing and all that. Because the simpler model you have, the more variance you have, right? So you add these two and you get this saddle graph. That is the generalization error. But this does not discuss an important thing. Okay, let me discuss this. Okay, how do we know, or what happens? What happens when you have a high number of training samples versus a very low number of training samples? Right? You have a very low number of training samples versus high number of training samples. So let me ask you this question. So you have this bias variance trade-off, right? So the error on test set versus model complexity is like this. The optimal model is somewhere here. Let's say that number of training samples is X, right? Now you have number of training samples X by 10. You have 10 times less training sample. What will happen to that saddle point? Where will it go? You have 10 times less training points. Will it remain the same? So will it move to the right or will it move to the left? And why? Right side means your right, means that's that way.
The system should become more complex.
To get better results. And you have 10 times less training data. So he says right. You have 10 times less training data, so system should become more complex. So that means the optimal complexity is at a higher complexity. Do you agree with it? Any other viewpoints? Yeah, if it doesn't go right, it will go left. So, any explanation if it goes left or not? Yes.
With less data, we're more likely to overfit, so it should go to the left.
Yeah.
Avoid this.
So he says with less data, we are more likely to overfit. If you have more complex model, it's more likely to overfit. So it should go towards the left. So which one is right? Which argument is right? Think about it. So if you have less data, how do we generalize? How do people generalize? Like, as human beings, we generalize. We see examples and we generalize, right? What makes us think? If I see one or two examples, will it make me think? If I see more examples, there will be more contradictions and I will think more. I need to think more. It may so happen that I still don't think more. But I need to think more, right? If you see more examples. That happens in science also. You have a hypothesis, it fits some examples, and suddenly you see another example that doesn't fit. So you need to think more and you have to have more complex hypothesis, right? But if you see simpler, lesser number of examples, then you can have a very good hypothesis that is tailored, that works very well with that example, right? And that hypothesis is much simpler because you don't have to think much. So I apply that concept here. So which means that if you have lower training samples, I don't have to think much and I will get a very good result. So that means the optimal model will have lower complexity if I have lesser number of training points. Versus if I have higher number of training points, I need to think a bit more because I have more variance, I have more complexity, I have more contradictions in my model. So I have to think more, so I need more complex machines. So if I have higher training set, the saddle point will go there, higher number of training set. The saddle point goes there. Versus if I have lower number of training set, the saddle point goes to a simpler complexity machines. Okay? So that is not discussed in the book. Okay, so now we have to do model evaluation. So there are performance evaluation, different performance metrics are there. There are different performance evaluation methods, and then how do we compare different models? So let's answer these one by one. So metrics, you know, false negative, false positive, true negative, true positive. Everybody knows this, right? And there is a trade-off, right? Trade-off between true positive and false negatives, right? So one increases and the other one decreases. Why though? So true positive versus false negative, right? So if you have higher true positives, then false negatives decrease. Whereas if you have higher false negatives, then true positive decrease. What is the reason?
Because the sum is constant.
No. Oh, sorry, I'm making a mistake. No, yeah. True positive plus false negative is constant. Right? I'm making a mistake here. Let me think. So true positive and false negative is what? It is positive, but it is classified as negative. So true positive plus false negative should be same. So true positive versus false positive. Oh yes, true positive versus false positive. Yes. Now I think it's correct. So if true positive increases, false positive also increases. Whereas if true positive decreases, whereas if you decrease false positives, then true positives also decrease. Now true positive plus false positive is not constant. Why does this happen? So I am reiterating. True positive versus false positive. What is true positive? True positive means the class is positive and the machine has classified it as positive. And what is false positive? The class is actually negative, but the machine has classified it as positive. Okay. So if true positive is increased, false positive also increase. But if false positive decrease, true positive also decrease. It's not like a property of data, but it's property of machine. So any technique you take to increase true positive, turns out it increases false positive. Any measures you take to decrease false positive, turns out it decreases true positive. Why does it happen?
Because you are shifting the decision boundary in one direction to make that happen.
So what?
The classification is optimal. Like if I am doing a true positive, every time I am doing true positive correct, that means that if I get a negative sample, it will be optimal.
So I get your drift. So what happens is that true positive more means you can think of it like this. This is not a mathematical reasoning that I am giving. It's just a hypothesis that I am throwing at you. That true positive, increasing true positive means that the machine is getting easier to get accepted. Right? So if it gets easier to get accepted, then that means negative points, which were classified as negative, they will also get easily accepted as positive. Right? So false positive will increase. And true positive decreasing means it is getting difficult to get accepted by the machine. So machine rejects more often. So if it rejects more often, then that means it will reject the negative ones also more often. So false positive will decrease. But not only that, true positive also decreases. So any measure taken to do this is always has this problem. There is a mathematical explanation, but you have to assume that the test set and training set have the same distribution. If the test set and training set has the same distribution, then this is true. True positive versus false positive. Right? But if it has a different distribution, then this may not be true. There may not be any correlation between true positive and false positive. If the training set and test set has different distribution. Now, this argument doesn't make sense. Why? Why doesn't it make sense? Because why will you consider that training set has a different distribution than test set? If you consider that training set has a different distribution of test set, then you cannot have any machine. Because machine does generalization. It assumes that training set is same as test set. Not same. The distribution of training set is same as test set. That is the assumption. So if you break that assumption, then yes, everything breaks. Okay. So you have a machine with the hope that training set has the same distribution as test set, and if you are doing well with training set, you will do well with test set. So that's why you will always have this problem that any measure taken to improve the true positive will also worsen the false positive. And any measure taken to improve the false positive will worsen the true positive. You will always have that trade-off. So that is with respect to this slide. Now the matrix that is used to calculate true positive, false positive is called confusion matrix. So you have yes, no, and actual versus predictive class. These are, I think you know already. Okay, another problem is accuracy. What is accuracy? True positive plus true negative, that is what you want. Right? True positive should be classified as positives, true negative should be classified as negative. So that is accuracy. So true positive plus true negative divided by total number of samples multiplied by 100. That is your accuracy. But this accuracy metric has a serious problem. Right? Serious problem with respect to class imbalance. Class imbalance means what? Let's say, let's take the example that you are using a wristband, you are identifying whether you are eating or not. And you are trying to identify the eating action. Now, eating action is rare. Rare means what? You eat and then you move the hand. So your non-eating related actions are much more than eating actions. So there is a class imbalance. So which means eating action has much less data than non-eating action. Right? Much less instances. So true negative is much more than true positive. So let's say out of 100 items, 97 items are true negative and 3 items are false, true positive. Right? So now if you have a machine that is always wrong, right? A machine that is always wrong, when you present it with a positive class. Right? A machine that always classifies everything as negative. It's a very simple machine, takes a test data and just outputs negative class. What is the accuracy? 97%. The accuracy of that machine is 97% and you are very happy. Right? But that does not cut the deal. Because any positive class data point you give, it will identify as negative. 100% error in positive class identification. So that's why when you have class imbalance, accuracy doesn't work. So you cannot use accuracy. That is what this is saying, class imbalance. So what do you use? You define, first of all you define rates. True positive rate, true negative rate, false positive rate, false negative rate. How do you define? Just true positive by true positive plus false negative, just a rate. You define rates and then use those rates to define these metrics, precision and recall. Right? What is precision and what is recall? Precision is true positive divided by true positive plus false positive. Right? And recall is what? True positive divided by true positive plus false negative. So this solves the problem of class imbalance. And because you are not biasing towards true negatives, you don't worry about true negatives. There is no true negative in precision and recall. Right? So this is good. So you use the precision and recall to identify positive class. So this will solve the class imbalance problem. And then you have F1 score. That is F1. Yeah, F1 score. So F1 score is a combination of precision and recall, and that's how you combine. It's just the geometric mean of precision and recall. Right? That is F1 score. So these are different metrics that are used to evaluate a model. And then you can have cost metrics. Cost metrics means you can have a more cost to positive class than negative class. So if you make error in positive class, you pay a penalty. Right? And if you make error in a negative class, you don't pay as much penalty. So in that way, you can associate a cost for misclassifying positive class. So that you can talk about cost metrics there. It shows an example of how do you compute cost of classification. So these I'm leaving you, you can understand these. These are just numerical things that you just read the slides, you get it. No point in discussing this. Then methods of performance evaluation, we have already talked about this cross validation. Right? Holdout, holdout is the one that I said that 2/3 is training, 1/3 is testing. That is holdout. And a more complex version of holdout is cross validation. Random subsampling means you just randomly sample or randomly do a holdout. You can do it with substitution or without substitution. Saying the same thing, we have already discussed this. So methods of model comparison. So now this is important. So if you have two models, two machines, how do you know which one is better? Right? How do you characterize these? So turns out what you can do is you can plot the true positive rate against the false positive rate. So that's where the trade-off will come into picture. True positive versus false positive. How should the graph look like? True positive versus false positive. So this is, if you are familiar with electronics, semiconductor diodes or transistors and semiconductor devices. If you look at them, what do you call it? You call it an IV characteristic, right, of a transistor, IV characteristic. How does it look like? It looks like this, this kind of a graph, saturates, right? If you go further, then it doesn't saturate, it becomes oscillator. But if you don't burn the transistor. So if you don't burn the transistor, it's just this, right? So depending, I've spoken so much. Yes, so depending upon the transistor characteristic, so you can distinguish between two transistors, right, using the transistor characteristic. So this is also like the same. So this is receiver operating characteristic. That means the transistor operating characteristic or ROC curve. So this is a plot with the true positive rate against the false positive rate. How does it look like? It looks like it's almost similar to a transistor curve. Right? Almost similar to a transistor curve. Now, what is the ideal curve? Can you tell me what is the ideal curve? Ideal ROC curve. So how much true positive do you want? How much false positive do you want? You want all true positive, right? And you don't care about the false positive. Even if false positive increases to 1, you still want all true positive. So how should the graph look like? Yes? How should it look like? Yes, exactly, a step function. So step function means you just shoot up V1 and V1 forever. Right? Now you understand, if I want to calculate the area under the curve, and if I want to calculate the area under the curve, if I have the best curve, the perfect scenario, what should be the area under the curve? 1. Right? So area of the ROC curve, the best is 1, but I never get 1. If I have that diagonal line, what does that mean? What does the diagonal line mean? So true positive is 50%, false positive is 50%. It means that no point in having a machine, or no point in having that machine. That machine is 50% right. So just toss a coin. Right? So your graph, your ROC graph should always be higher. It should be superlinear. Right? It should always be higher. Shouldn't use the term superlinear because that means it goes up. But it should be always above that line. It should be always above that straight line. Right? And the best is that hump should go up to 1. So as sharp of a curve you have, the better. Right? So that is ROC curve. These are two different machines, M1 versus M2. So you see that M1 is better for low false positive rates. If you have low false positive, then M1 has better true positive rate. Whereas if you have high false positive, then M2 has better true positive rate. So two machines might be well suited for different purposes, right? So you might not use a single machine for your entire application. You might need to use different machines based on what is more important to you. Is false positive more important? Do you want to reduce false positive? Right? If you want to have minimal false positive, that is your concern, which machine will you use? If you want to reduce false positive, because in your system you cannot have false positive. What is an example? An example is biometric authentication. You cannot have false positive. Nobody else can come and give their fingerprint and act as if like you. And that is false positive. So in biometric systems, which machine will you use? M1 or M2? M1, right? Because for low false positive rates, M1 has much better true positive rates than M2. On the other hand, you have a high false positive rate. In case of high false positive rate, so where is a good example of high false positive rate? Where do you want high false positive rate? For example, in premature babies, right? When you have an algorithm running in premature babies to detect bradycardia. Bradycardia means the heart rate slows down and the baby has breathing problems. Right? So in that case, you don't worry about false positive rate. Right? However many false positive I am okay, I can go and check on the baby. Right? But you want to worry about true positive rate. So in that case, true positive should be 1. It will be much more. So in that case, which machine will you use? You will use M2 because at higher false positive rate, true positive is more for M2. So ideal area is 1, random guess area is 0.5. Right? So you should have area under the curve for ROC greater than 0.5. If you don't have greater than 0.5, there is no point in using that machine. So how to construct an ROC? No need to know. Right? And you can, if you are interested, you can read the book, but it's a very old thing. So I will stop here actually with classification. The next time we will start with alternative methods of classification, which means we will talk about time-based, support vector machines, random forest, and so on.